Guys, we are going to talk about continuity and limits and the intermediate value theorem. Okay? Now, first of all, this idea of continuity is so important, and we're going to talk a lot about why that is and really study this concept. It's so important. But, if you think about it logically, what does continuity mean? It does make sense. So let's take a look at some graphs to kind of paint this picture for us. Okay, so we have three graphs here. It says these are the three conditions exist for which the graph of f is not continuous at x equals c. So at a point, it's not continuous. So for example here, f of c is not defined. You guys notice that at c there is no y value that's defined. So this is an example of where we have discontinuity. Here, the limit of f of x as x approaches c doesn't exist. And, we studied already why this limit doesn't exist at c. It's because the left-hand limit and the right-hand limit don't equal the same thing. So that makes sense. And then here, the limit is not equal to f of c. So while the limit does exist, it's not equal to the function's value at that point. Okay, this is called removable discontinuity, right? So all three of these are cases where we don't have continuity at a point. Anytime I think about the word continuous, just think, can I trace this graph with my pencil and never have to pick my pencil up? And in each of these cases, I would have to pick it up. Okay, so an actual formal definition. So definition of continuity here. So we have continuity at a point, and that's what those three cases we're kind of outlining here. So a function f is continuous at c, so at a point, if the following three conditions are met. First of all, it has to be defined, right? Just like in that first scenario. The limit has to exist, and the limit must equal the function's value at that point. Makes sense if you guys take a look at those pictures above. We also can define continuity on an open interval. A function is continuous on an open interval, a to b, if it is continuous at each point in the interval. A function that is continuous on the entire real line, so infinity to infinity, is continuous everywhere. Let's kind of talk about what it means to be an open and closed interval, because you're going to hear that a lot, and it's important for us to know. So open interval, remember, just means we don't include the endpoints, so a to b. So maybe I should write that down. No defined endpoints. So visually speaking, like let's say I have A, let's say I have B, and continuous, whatever that shape in between here, it's continuous everywhere between A to B. So that's my open interval A to B. Now if we're talking about a closed interval A to B, now we do have defined endpoints. So I have closed point, A, B, so they're included now. Whatever is happening in between the two, well, we have a closed interval here. Okay. Technically what it was saying in that open interval definition about negative infinity to infinity, technically negative infinity to infinity is an open interval because negative infinity and infinity are not actual values that we can get to like we could in a closed interval here. So technically, negative infinity to infinity is an open interval. Oops. We can also have a definition for continuity on a closed interval. So very similar, except this one does have something special about its endpoints. It says a function is continuous on the closed interval if it is continuous between a and b, and the right-hand limit is equal to f of a. The limit as x approaches a from the right of f of x is f of a, and the limit of f of x as x approaches b from the left is f of b. In other words, the function f is continuous from the right at a and continuous from the left at b. And here it's a good figure to help understand that. So some more important words. Discontinuity. Something's not continuous and it's discontinuous. It says consider an open interval I that contains a real number c. If a function f is defined on I, except possibly at b, and f is not continuous at C, then f is said to have a discontinuity at C. This is kind of wordy, but just understanding what it means to be discontinuous. Removable discontinuity, okay? A discontinuity at C is called removable if f can be made continuous by appropriately defining or redefining f of C. So in other words, think of a hole. Okay, so we had a picture of that before. And then non-removable discontinuity. A discontinuity where f cannot be made continuous. So think vertical asymptote. Okay. Another case where this can happen is if you have a jump for non-removable discontinuity. We have some properties of continuity, okay? Seeing similar properties in different scenarios, but now we're talking about them in terms of being continuous. It says if k is a real number and f and g are continuous functions at x equals c, then f plus g, f minus g, f times g, k a constant times f, and then their quotient, assuming that g of c is not 0, are also continuous. All this says is if we add, subtract, multiply, divide, or multiply by scalar of two continuous functions, then their result will also be continuous. Okay, that's all this says. And then last but not least here, it says the following types of functions are continuous at every point within their domain. So for example, we know all polynomial functions are continuous everywhere. All rational functions are continuous everywhere in their domain. And all radical functions are continuous everywhere in their domain. The key thing here is the in their domain part. Remember, for example, the domain for polynomial functions is all real numbers. But the domain for rationals aren't all reals. So for example, if I had f of x equals 1 over x, 0 is not in the domain. There's an asymptote at 0. But it's continuous everywhere in its domain. And then same with radicals. Okay, so let's practice a little bit. It says for the function at the right, find the limit of f of x as x approaches c from the right, as x approaches c from the left, and as x approaches c. And then let's have you answer questions D and E as well, and then we'll check our answers. Go ahead and put me on pause. So first we have to figure out what are these three limits. So in order for the limit of f of x as x approaches c to exist, these have to both equal the same value, and they do. So all three of these have limits at -2. So is it continuous at c? Why or why not? Yes, it is. And if we go back to that definition for continuous at a point, there's three things that must be true. First of all, f of -2 has to be defined. Yes, it is defined. Also, the limit has to exist, which right here, kc, yeah, the limit exists. And then the third thing has to be true is that the limit must equal the function's value. Also, looking at the graph, at -2, could I draw without having to pick up my pencil? Yes. And then part E says, is there removable discontinuity? Doesn't apply. Let's have you guys try this one. Go ahead and put me on pause. So, first and foremost, we're looking to see if the limit exists at -2. And since the left-hand and right-hand limit both equal 2, the limit is also equal to 2. As we approach -2 from the left and -2 from the right, it approaches positive 2. Man, so many 2's. Also note that the function's value at -2, though, is defined at 3. So is the function continuous at c? Why or why not? Well, visually speaking, if I trace over, I'd have to pick up my pencil. So clearly no. What's a good reason for this? Well, which part of the definition for continuous at a point does it violate? It violates that third condition. The limit does not equal the function's value. This would be the perfect answer. Yes, it met the first and second requirement, but not the third. And it has to meet all three in order to be continuous. Is it removable discontinuity? Yes. Remember when we talked about removable discontinuity, for this equation right here, this function, we could come up with a different function that is exactly the same everywhere, except for where the discontinuity exists. So in other words, we could come up with another function that is the same except at -2, which is where the discontinuity is, and we could make it continuous, right? So that's why it's removable discontinuity. All right, let's have you guys try this one. Go ahead and put me on pause. So right away, you guys can see the problem. The limit doesn't exist, so it's clearly not continuous. Is this removable discontinuity? No, because I couldn't have the same function except for at -1 and make it continuous. All right, is f of x equals the absolute value of x continuous at x equals 0? Prove it. Use the definition to show me. You don't have to do a geometry proof, but just show me why is it continuous. Go ahead and put me on pause. So 3 conditions or 3 requirements that must be met in order for a function to be continuous. The function must have a defined value at 0, in this case, check. The limit must exist, check. And the limit must equal the function's value at that same point, check. Okay, here's a fun one. It says, what value of a makes this function continuous? I'm not going to give you any hints, so think about it. All right, go ahead and put me on pause. Really helps to understand what's going on here. Now, clearly this is a piecewise function, and something important for us to recognize is that this piece is a polynomial and this piece is a polynomial, which means that both of these pieces must be continuous everywhere. And we're trying to make it continuous. We're trying to make these two be continuous at -1. Okay? The only possible place that we could have discontinuity is where we jump from one piece to the other, which is at -1. So that's why we want to make these equal each other at -1. So first and foremost, well, what is f of -1? Where is it defined at -1? At -1, right? Plug it in. So how can I make this equal -1? Well, let's just plug it in, duh. And we plug in -1 for x because that's where we're at for our x value. We just got to figure out, well, what's a? And we get a is -3. Okay, continuity of a composite function. It says here, if g is continuous at c and f of continuous at g of c, then the composite function given by f of g of x is continuous at c. Okay, so let's take a look at this example. I think this will make more sense. It says, discuss the continuity of h of x if of h of x equals f of g of x. So, a couple ways we could do this. Now, all this is really asking is to think about what will the continuity of h of x be, knowing that these are continuous on their domains. So let's figure out, well, what is h of x equal to? H of x is equal to f of g of x. So it's the square root of x squared, which is equal to the absolute value of x. So where is this continuous? It's continuous for all real numbers. Again, we're just discussing where this is continuous. Let's look at this one. So if I find h of x here, let's have you guys find h of x. Go ahead, put me on pause. Find the composite function, we get x minus 1, where x is not equal to 1. So this is continuous for all real numbers except x equals 1. This is also, note, removable discontinuity at x equals 1. Why? Because since h of x is a polynomial, it's possible to write this polynomial so it does exist at x equals 1. Don't forget, the domain of composite functions is restricted by the function we plug in. That's from first semester. Put me on pause. So watch my intermediate value theorem video. It's real short. Bye.